Okay, guys, so let's see. I'm gonna first start by talking about Project 3 a little bit again. So just answering some of the most common questions I'm getting. The first one is for part 2. How do you guys pick the right sizing for this NMOS? Remember, this is to get this part we're trying to get this drain. We're trying to get this drain capacitance per unit width. Okay. So the first question is, how do you pick the sizing for this design device M1? And I would always use length, minimum length, which in this case is 0.18 micron for all your transistors in these simulations. For the width, I'm assuming you guys are you've picked some unit device here, and you're basically increasing the width with M factors. And let's assume you're doing that. So I'm just going to talk about the total width you would end up with. Theoretically, you could make it any width, but because in the end, you're going to divide it by the width of the device to get the capacitance per unit per micron. You're eventually going to get something in terms of like femtofarads per micron. So, it doesn't theoretically doesn't matter, but in my opinion is maybe you should try something in the, I don't know, maybe like 50 to 100 micron width range, just so that your rise times here and here are, if it's something, that kind of capacitance, your rise fall times might be a little bit slower. So let's say so this guy would be, so let's say the red would be D, and um, this would be E or something, the node E, so E and D. So if these guys are a little slower, it's a little easier to, eyeball them, trying to get them to match, as opposed to if they're both extremely sharp curves, for example, and that would be the case where you have very little, where your devices are pretty narrow, in which case it'd just be harder, I think. It's easier to make a big mistake in terms of eyeballing, where at what value of C delay the two are sitting on top of each other. So again, I would suggest to make them in the 50 to 100 micron range. Sorry, so 50 to 100 micrometer width. Okay. The second question I got is, how do you decide on the transistor area drain, um, area source, perimeter drain, perimeter source? Okay, which is a parameter you have to plug into this device to get some, you're gonna want to get the parasitic capacitance of the drain source. And you got to remember how a transistor is laid out. Okay, so the transistor is laid out, here's your poly gate. Here is your active. And here are your contacts. So what we're trying to do is to get the area. First of all, it's okay to assume the area of the drain. It's equal to assume in this case that these area drain is equal to the area source, and perimeter of the drain is equal to the same as the perimeter of the source. We don't have to make any assumptions about, funky layouts, etc. So basically what you want to do is to come up with the area of this guy and also the perimeter of this guy. So this size is, you guys already have it. It's the width of whatever unit device you're using, so you can use that. So if it's, you've picked a 0.3 micron unit device, you can use 0.3 for this direction. For this dimension, you're going to have to use the design rules. So remember that, again, you're getting this area. So you have a certain spacing from the active to, sorry, between the active contact and poly. I'm not sure, I think it's 1 lambda. Then there's the width of the contact itself, which might be 2 lambda. And then there's the overlap of active over contact. And I think that might be 1 lambda, but take all that with a grain of salt. You might want to double check that. So all that adds up to what the minimum height here. So you get the width times whatever you come up with the height, and that gives you the area, and you add all 4 edges and you get the perimeter. And again, remember that the area should be giving you something. Remember, you're multiplying 2 numbers that are in the perimeter of something, x times 10 to the minus 6 times, y times, sorry, you have, whatever it is, x times 10 to the minus 6 times y times 10 to the minus 6. So the area, remember the area units should be, the AD units should be something times 10 to the minus 12. That's easy to screw up, and if you put in 10 to the minus 6 or something here for your area drain, area source, or worse yet, nothing at all, you're going to get some huge capacitance at this node, and you're going to see a real result. And then the perimeters are all 10 to the minus 6 getting added, so that should be more like 10 to the minus 6. So that's for number 2. Number 3, I think for the derivation of this, you could take a look at the book, and this is section 8.4.5. But this is doing a differential measurement. So you have one inverter with unit NMOS and sort of unit twice the unit PMOS, and you do 2 simulations. So you have, let's say you have one simulation where, let's say here's this point A and this is point B. Let's say A is doing this. This is time. This is voltage. So A is doing that. Let's say B is, so B, the first simulation you do is for H is equal to 3. That means you make this minimum, this M factor, or you make this unit device 3 times bigger than the unit, and make this 6 times bigger than the unit, and that'll have some fall, and you'll get some prop delay. This is prop delay falling. For H is equal to 3. And then you do a second simulation, and you do the same thing exactly, but you change the H to equal to 4. So you're doing H equal to 3 and H equal to 4. So H equal to 4 will have some other prop delay. So this is T prop delay fall for H is equal to 4. And you basically subtract, so this is this guy, you subtract this is the prop delay falling for H equal to 4, sorry, pointing at the wrong thing. Remember, the prop delay is 50% of input to 50% of the output. So basically you have for H is equal to 4. So basically you're subtracting this from this, and that gives you this number. and you have R sub n from, no, that's what you, sorry, R sub n is what you want to calculate. You have C, which is the gate capacitance from uh, from 1 here. Okay, so you calculated that or measured it, however you want to look at it. And now you have this value, which is the difference between these two simulations of h is equal to 3 and h is equal to 4. And remember the delays from here to here is what your prop delay, and 50% to 50%. And that's equal to 3 R sub n C, and you're trying to solve for R sub n. You do the same for rising prop delay, and so that just exactly the same thing, except you are looking at time voltage, and then your input's doing this, A, and you've got two cases. One of them is doing that for H is equal to 3, and the other one's doing this for H is equal to 4. And you want to get that minus that, and that'll give you this value. Okay, that was all the sort of the questions you guys had. I hope that's useful. Um, I'll post this and then send you guys a recording of the lecture. Thanks. Bye.